right, today we're going to talk about plate tectonics, and as we'll learn, plate tectonics is a really fundamental piece of our understanding about the Earth system that influences a lot of other geologic processes, such as volcanoes and earthquakes that we'll talk about later. So before we refer to the process of plate tectonics, there were scientists who had explored the idea that the continents were moving around and that the current position of the continents is not the same position that these continents had always occupied throughout geologic history. And in particular, there was a famous scientist named Alfred Wegener who lived about a century ago, and in 1915 he wrote a book that was called The Origin of Continents and Oceans. And in this book he laid out his hypothesis for the fact that the continents today occupy a different position than they had in the past. And in his book, he in particular identified that there had been a time in geologic history about 200 million years ago when most of the continental masses that we know of on the Earth today were joined together in a supercontinent called Pangaea. And then since that time, he hypothesized that the continents had been moving apart from each other and eventually had come to occupy their current position. However, he couldn't really explain the mechanism for how the continents had moved apart from each other, and so this was a pretty big thing for people to accept, and it was never widely accepted by the scientific community during his lifetime, even though he had some pretty strong evidence to support the idea that the continents had previously occupied different positions. But again, he just had trouble explaining the mechanism, and so he was never really able to gain the acceptance that he was hoping for his new theory. He referred to this process as continental drift, and of course today we know that the continents really aren't drifting around, they're being pushed and pulled around by different processes below the Earth, and today we think about the movement of these pieces as plate tectonics. So what our current understanding of plate tectonics tells us is that the Earth's surface is made up of around 15 rigid lithospheric plates that slowly move around over the flexible asthenosphere. So hopefully you'll remember that the lithosphere is the surface layer of the Earth that forms a rigid, hard, solid layer, and it sits above the asthenosphere, which is a slightly flexible, more putty-like layer that circulates slowly over time due to convection and heat circulation underneath the planet. So these rigid lithospheric plates are moving around on top of this flexible material. And as this happens, the surface material of the Earth, particularly the oceanic lithosphere, is constantly being recycled. So new oceanic material is expanding and old oceanic material is disappearing into the Earth and being recycled. And we'll talk about the details of how that works later on, but today plate tectonics is a very widely accepted and fundamental piece of our understanding about geology and basic Earth function. And on the slide you can see a map of some of the major Earth plates. So you can see, for instance, the African plate in the middle of this diagram, the Eurasian plate, North American plate, etc. And hopefully you can also observe from this map that many of the plates contain both oceanic parts and continental parts. So the African plate contains the continental material of Africa, but also contains a lot of the ocean floor around that continent. And that's not unique to the African plate, but other plates work the same way as well. Then you can also see the arrows showing the directions that different plates are moving. So they're moving in all different directions, and then also the speeds at which the plates are moving, which vary. So the Pacific plate is moving the fastest, and then other plates are moving a little bit slower. So the reason that the plates appear to be moving is that there's a lot of heat energy inside the Earth And this energy is moving around. The heat is rising up from the depths of the earth where it's very, very hot in certain places. And as that heat comes up to the surface, it is pushed outwards through the asthenosphere. And since the asthenosphere is slightly plasticky, it can move very slowly over time. And so as it moves, it circulates heat outwards from certain places. And those places from which heat is moving we refer to as divergent boundaries that we'll talk about later. And then in other places where the asthenosphere has cooled off, then heat is actually sinking back down into the earth. And along those areas, we have convergent boundaries and in particular subduction zones that we'll talk about later. And most importantly, as the heat is causing the asthenosphere to move, the lithosphere, the rigid parts of the surface of the earth that sit on top of the asthenosphere, are moving with the underlying asthenosphere. So convection is that mechanism that Alfred Wegener couldn't explain a century ago, and we commonly refer to this mechanism today as seafloor spreading, because commonly we see these areas where the asthenosphere is moving apart from each other, the ocean is diverging, and new lithosphere is actually being created. This commonly occurs in the oceans, and so this is commonly referred to as seafloor spreading. So there's a couple pieces of evidence that support our idea of why this is occurring. There's actually more than a couple, but we're just going to focus on a few in here today. And first of all, we have talked earlier in this class about GPS technology, global positioning system technology. And so the reality is today we can put sensors that communicate with satellites on different solid parts of the Earth's surface, and we can track very accurately how they're moving around. And we can see that in fact the different parts of the Earth are moving, they're moving in different directions, and they're moving in different speeds relative to one another. And so that confirms our notion that plate tectonics is definitely occurring. But there's a lot of other things about the Earth that had indicated to earlier scientists that this process was going on as well. And one of them is the fact that the age of the rocks in the ocean floor is not all the same. And in fact, the age of the rocks in the ocean floor has a pretty interesting pattern. And that pattern is that the age of the ocean floor expands away from mid-ocean ridges, these zones of mountainous volcanic ranges that exist out in the middle of the oceans. And the very youngest rocks exist right near the volcanoes, where new lava flow under the ocean is creating new rocks. And the farther that we move away from those mid-ocean ridges on either side, the older the rocks get. And they follow this kind of pretty clear mirror image pattern on either sides of the mid-ocean ridges. And this is something that indicated to scientists that perhaps these mid-ocean ridges were actually sources of new material, and that new lithosphere was being created in these locations, and then it also must be disappearing in other locations. So the oldest rocks that we can find in the ocean are shown on this image in dark blue, and these rocks are about 180 million years old, which might seem old to you, but if we remember that the Earth is more like 4.6 billion years old, and we know that a lot of rocks on the continents are about or at least over 4 billion and 3 billion years old, then 180 million year age is relatively young. And so the rocks in the ocean that seem to be coming out of these mid-ocean ridges must be also disappearing and being recycled somewhere else. And we understand today that that is along certain convergent plate boundaries. We can also see that heat rises up into these mid-ocean ridges, the same places where we have the really young rocks, and that's another indication of this convection process that we talked about before. And again, we can actually today track the rate at which these plates are moving with new technology such as GPS units, and so we can see exactly how fast these different pieces are actually moving and also in which direction they're moving. And something that might help you remember how fast this occurs is that the average plate motion is a few centimeters per year, which is about the rate at which your fingernails grow. So here's a photograph of a man who holds a world record for the longest fingernails. Pretty long, seems probably pretty inconvenient to carry around that much fingernail with you in your life. But you can see that this amount of distance for a plate to travel is not the kind of thing that you would see in any given day, but it is something that accumulates over time. And this is how much accumulation has occurred in this man's lifetime. And then if we think about geologic time, right, which occurs over millions and billions of years, you can imagine that this rate of travel can add up to quite a bit of distance being covered by pieces of continent and ocean. And here's another comic on the left saying, hey, I'd like a tectonic plate. Very good, sir. That may take a while to get here. So just some dorky science comics for you today. Okay, so when we want to think about the mechanics of what happens along these different plate boundaries, we are going to need to understand that there's some differences in the material that makes up the continents, which form certain parts of plates, and the oceanic material that forms other parts of plates. And so I have some differences outlined here on the left, but basically the rocks that make up the continental crust, which is kind of the upper part of that rigid lithosphere layer, are thick. They can be somewhere between 20 to 75 kilometers thick, so a lot thicker than oceanic material, which may be more in the range of 5 to 10 kilometers thick. They also tend to be made up of materials that are lighter and less dense than the rocks that form the ocean floor. And then also, as we've already discussed, the ages of the rocks in the continent tend to be on average quite a bit older than the rocks that make up the ocean floor. So the oldest rocks in the ocean we said are about 180 million years old. MA stands for million years, while we have rocks on the continent that are nearly 4 billion years. So GA is a shorthand that geologists use to refer to giga-annum or billion years. So a lot older rocks on the continents. Those rocks seem to be sticking around over time, while the oceanic, denser, thinner rocks seem to be recycled over time. And you can also see a diagram on the right here showing the thinner, darker, denser rocks that form the floor of the ocean with some water that has built up on top of them, compared to the thicker rocks on the left-hand side that make up continental material. So now that we know that, let's try to think about what are the kinds of processes that occur along different plate boundaries. So the first kind of boundary that we want to think about is a divergent plate boundary. And divergent means two things that are moving apart from each other. And so we see divergent plate boundaries at locations where two plates are moving apart from each other. And we saw some diagrams a few slides back of this and said that this would occur because of convection and heat circulation underneath the Earth's surface rising up and then spreading out in two different directions and kind of carrying some asthenosphere with it in opposite directions that then therefore carries overlying lithosphere in opposite directions as well. So in the places where this is occurring, we tend to see volcanic activity along the place where that heat is first emerging onto the surface. Those volcanoes are creating new rocks, and those new rocks are sliding outwards over time, and then the older rocks start to exist at locations that are farther and farther away from the sea floor spreading center, or that mid-ocean ridge. And so you can see the diagrams at time 1, 2, and 3 here show that the new rocks that exist at the center at any given point are being pushed farther and farther away from the mid-ocean ridge as younger and younger ocean is growing in between. And if that oceanic floor is fused with the continental pieces on either side, so if the ocean and the continent are making a joint tectonic plate, which we often see like in the case of the African plate or in the case of the North American plate, then as this seafloor spreading occurs, or as this divergence occurs, the expansion of the ocean will actually push the continents around with it. So when Alfred Wegener was talking about continental drift or drifting continents, he didn't quite have the concept right, because they're not drifting. They're being pushed around by the divergence of plates along these seafloor spreading centers. So here's some images of what it might actually look like if we were under the ocean at a seafloor spreading center. On the top we see a scuba diver who's swimming around through these volcanic rocks. These are called pillow basalts that would be erupting in and existing kind of in the vent at the top of a volcano underneath the ocean. And then on the bottom we can see what are called hydrothermal vents, or these hot water vents where water that's very, very hot is streaming out of the rock formations there, heated up by magma underneath the ground that's fueling these volcanic eruptions. And these locations actually support these very unique and very interesting ecosystems that exist underground, way far away from any sunlight, and the organisms that are down there exist in this special ecosystem that depends on a chemosynthesis process instead of a photosynthesis process, where the organisms are using chemicals to gain the energy to support the food system. So these are pretty neat things that you might have heard about in a biology class, or you might want to explore more later on. But these are the kinds of things that we might see if we were down underneath the ocean at a seafloor spreading center. In addition, sometimes we actually can observe these processes happening on land, on continents. And in particular, these processes often begin on continents and then over time actually build the space for new oceans to be created in the place where a continent had previously existed. So, for instance, we see this going on in East Africa, and the location where the Red Sea existed or exists today is basically the expansion of a new ocean that might be quite a bit bigger in the future. And a little bit farther south into the kind of the Horn of Africa and lower down in East Africa, there's an area that's referred to as the Rift Valley, where the continent is rifting or pulling apart from each other. There's many low points on the landscape here that are created as the continent is pulling apart, that are filled up with water. And these form these big lakes, like Lake Tanganyika in Africa. And there's also a lot of famous volcanoes in this area, like Mount Kilimanjaro. You may have seen pictures of that or heard of that before. Mount Kenya, another one. And this landscape is being created as the Horn of Africa is actually pulling away from the main continent of Africa as a result of this convection that's occurring in the earth below this location. We actually see a similar process occurring in North America, where the area of the Rockies and the area to the west of that, like places like California, the Sierra Nevada, where we live, these two locations are actually pulling apart from each other over time. And we can also see, if we look at a geothermal map, a map of heat and underneath the earth, that there's a bunch of heat that's rising through convection into this Great Basin area or basin and range area that forms Nevada, parts of Utah, California, Arizona, etc. And that is actually fueling the stretching of the continents in this position. So it's possible that we could come back in 20, 30 million years and see a new ocean opening up in this particular location. Okay, so that kind of covers what we see in divergent areas. But another thing that can happen is that continents can be, or not just continents, but plates can be colliding with one another or converging with one another. And there's a variety of different outcomes that can occur along these convergent zones, and it depends on whether the material that's converging is oceanic or continental in nature. So first we'll talk about what happens when we have a plate boundary where there's oceanic material on one side and continental material on the other side. And so this diagram shows oceanic material on the left, continental material on the right, and then you can hopefully see by this diagram that the oceanic material is moving towards the continental material, so they're converging or colliding. And what happens here is something that's called a subduction zone is created. So before we discussed that oceanic crust is thinner and more dense than continental crust. And so when the oceanic crust butts up against the continental crust, the bigger, thicker continental crust will end up sitting on top of the oceanic crust, and that thinner, denser oceanic crust will end up sliding below it. And it will eventually get pulled down into the asthenosphere, where it will be recycled into the material of the Earth. But as it does this, as it subducts or bends down below the other continental plate, it carries down things like ocean water and different gases that are dissolved in ocean water in these little cracks and fractures along the surface rock that's subducting. And these materials that are sometimes referred to as volatile materials, but you can also just think of as kind of ocean water, end up changing the nature of the rocks as they start to subduct and go to deeper and deeper depths within the Earth. And in particular, what happens is that the introduction of this water allows the rocks to melt at a lower temperature than rocks would normally melt. So you can see in this diagram that at different depths, around 200 kilometers, most of the asthenosphere just looks brown and is solid. It's not melting. But right on top of the subducting plate, there's a zone that looks red, and that indicates that those rocks are melting. And the reason that they're melting is because the water is allowing those rocks to melt at a slightly lower temperature than would ordinarily be necessary. And once that magma, that melted rock, forms, it starts to bubble up through the asthenosphere and the lithosphere, and eventually reaches up to the surface, where it blisters up on the surface and erupts in volcanoes that create these essentially blisters along the surface that we see as volcanoes today. And along a place where a plate is subducting, we may have an entire range of volcanoes that are kind of lined up, and many of these volcanoes in this volcanic arc may be active within the same kind of time frame. So you can see two different volcanoes in this particular diagram that are both active at the same time. So this is the kind of thing that we see along a subduction zone. And in addition, we would see earthquake activity occurring as this plate is being dragged below the other plate. And we would see that these volcanoes are positioned in a certain way so that they're typically about 100 kilometers away from the place where the plates are actually originally meeting. So in divergent zones, we see volcanic activity really right along the plate boundary. And in this case, we see volcanic activity that is offset from the plate boundary, always on the overlying plate, and always a pretty similar distance, around 100 kilometers away from the boundary position. So here's a photograph showing a bunch of volcanoes that exist in a volcanic arc that's created by subduction. And these are some of our local or relatively local volcanoes. This is Mount Hood, Mount St. Helens, Mount Adam, and Mount Rainier that all exist in northern Oregon and southern Washington. And they're part of the Cascade Range. And then I have a kind of a diagram of the Cascade Range here. And you can see that there's a bunch of volcanoes that are not perfectly lined up, but that are pretty well lined up about 100 kilometers inland from the coast of North America, and in this particular place, the coast of North America is a plate boundary where the continental material in the North American plate butts up against oceanic material on this small plate called the Juan de Fuca plate that is subducting under Northern California, Oregon, Washington, and British Columbia, and creating these volcanoes in the process. We can also see subduction when we have two pieces of oceanic material converging with each other. And in this case, the process is essentially the same, that one of the pieces of ocean will subduct under the other. It's usually the older piece of ocean that subducts below a younger piece of ocean. But beyond that, it carries down water, creates magma that bubbles up to the surface in the same way that we see in continental oceanic subduction zones. But the volcanoes that it creates originally exist under the water. And then if they get big enough, if they continue to erupt and spew enough material, those structures that they create may get big enough to come up out of the ocean and create islands. And sometimes these islands can really be quite big. So, for instance, Japan is created along a subduction zone. So that's some pretty significant land masses in that country. And the Philippines is also an area that's created by subduction. So I like this photograph because you can see that the Philippines is an island, or is a country that's made up of many islands, and these islands are volcanic, and so you can see quite a few volcanoes just in this one photograph. There's a volcanic crater right in the foreground, and then one a little bit behind that on the same kind of island structure, and then there's another volcano in the distance. And so this gives you an idea that this entire country and this entire landmass is actually created through volcanic eruptions that have built up material over time. All right, the final thing that can occur where two plates are colliding or converging with one another occurs when both of the pieces of material on either side of the plate boundary are continental. And as we've discussed before, the continental crust is pretty thick, can be up to 75 kilometers thick, and the entire lithosphere, the whole rigid part, can be even thicker than that. And so basically those pieces are too thick and too buoyant to be shoved down under another piece of lithosphere. And so when they collide with each other, instead of one piece basically bowing down below the other, the pieces just start to crunch and crumple as they continue to run towards each other and collide with one another. So sometimes people kind of use the analogy of beer cans or soda cans kind of crunching up and bending and creating a bunch of folds if you push on the ends of these different kinds of aluminum cans. And what we see in these areas is that there's a lot of bending and folding of the rocks, and then these rocks, as they bend and fold, end up sticking up way up high above the landscape. The folds also stick down below into the asthenosphere, and this kind of activity, you can probably imagine, creates a lot of earthquakes, but there's actually no source of magma in this environment, and so we don't usually see these ranges as being volcanic ranges, but instead there's just these dramatic mountains that are created by crumpling of these two colliding plates. So the most famous place where this occurs on our planet is the Himalaya. So this is in Nepal and Tibet, parts of China, Pakistan, Afghanistan, and Mount Everest, which is kind of on the right side of this particular image, is probably is the tallest mountain in the world. You've likely heard of that place before. But I also like this photograph because it shows that Mount Everest isn't alone. It's not sticking up as a peak out of nowhere, but it exists in this entire landscape of many, 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 many mountains that are spread out along hundreds of miles of this region. And these mountains are created by the crumpling of the crust, by the collision of these two continental pieces. Another thing that's interesting about this zone is a lot of the rocks that make up the mountains in the Himalaya are a unique type of rock called limestone, and limestone is a rock that's created from broken down pieces of old coral reefs and other kinds of seashells. And it's kind of interesting that this region, the Himalaya, which is not near the coast today, would be made up of these kinds of oceanic or marine rocks. And our understanding of why that occurred is because the area where the Himalaya exists today has been created where what's called the Indian subcontinent or the Indian plate collided with the Eurasian plate. And so today these areas are fused into one big continental area. But 50 million years ago, India was its own separate piece, and it had coral reefs and lots of marine environments along its north coast. Those areas formed limestone, and now that the Indian subcontinent has collided with Eurasia, those marine rocks are forming the peaks of the mountains in this high mountainous range. So I visited Nepal about 10 years ago and spent some time there, and I was interested to find out that there was lots of marine fossils in that environment. A lot of the local people make really cool and beautiful jewelry out of these different kinds of marine fossils. And again, that represents the idea that in the past, that region was actually a coastal region, which is very different than its condition today. All right, so the last kind of boundary that we want to mention is something that's called a transform boundary. And a transform boundary exists in locations where the two plates along the boundary are neither really moving apart from each other, we call that divergence, nor are they colliding with each other, we call that convergence, but instead they're kind of moving in opposite directions. So they're kind of bumping shoulders as they move past each other, and kind of a transverse way. So you can see in this diagram, these arrows are pointing in opposite directions. And California is a famous or potentially infamous location where this kind of transform activity occurs. And not all of California experiences this type of motion. We already mentioned that the very northern part of California exists along a subduction zone. But Central and Southern California exists in a transform boundary location where the North American plate is moving in an opposite direction from the Pacific plate that exists off to the west. So you probably know that California is infamous for having a lot of earthquake activity, and these earthquakes occur as these plates are rubbing shoulders with each other, rubbing against one another. They're getting caught on one another, and then they're stretching, and then they're snapping forward, and those events cause big earthquakes. So I have some photographs here showing a big tear in the landscape on the bottom left that occurred in the area north of San Francisco after a big earthquake there in 1906. On the right, you can see a big scar on the landscape where repeated earthquakes have created this big tear or scar, and this zone is called the San Andreas Fault, which you've likely heard of before. San Andreas Fault is a location where we experience lots of earthquakes in California as the North American plate on the right moves in a separate direction from the Pacific plate that's on the left. So interestingly, there's also parts of coastal California that are land that are actually not on the North American plate, but are actually attached to the Pacific plate instead. And those places are moving in a different direction than the rest of the North American continent. And you can drive across the San Andreas Fault in many places, particularly in Southern California, and here is a picture of a sign indicating that you're moving from one tectonic plate to another. So to kind of wrap up our discussion of this kind of thing, I just want to show you a change in the shape and orientation of some different continents over geologic history. So this particular series of images starts 550 million years ago, and right in the center you can hopefully see that there's outlines of many of the states in the United States of America and provinces up in Canada that exist today. So you can see that North America wasn't the same size or the same shape that it is today. The western states weren't part of North America, nor were some of the southern states and places like Florida. You can also see that there's a white line on the left-hand side of the screen that shows the location of the equator and then has an arrow pointing north. So not only was North America not the same size and shape that it was today, but it was also in a different position on the globe in the past than its current position. So here's, again, 550 million years ago. Then here's 430 million years ago. And you can see some different kinds of island chains that are being created out in the ocean, probably by subduction of one oceanic plate under another. Then you can see that the continent of North America is rotating up and starting to cross the equator. And this island chain to the west of North America is coming closer to North America, likely as the oceanic material in between the islands and the continent is subducting. 385 million years ago, 330 million years ago, you can see that, again, these islands to the west of North America are starting to join up with and add on to the western part of North America. And on the southeast side of North America, you can see that it's slamming up against some other continents. And so this is when that supercontinent that we referred to earlier, Pangaea, started to form. And that created a lot of continental collision, similar to what's going on in the Himalayan region today. You can see a lot of mountains forming in that area where that occurred. And some of those mountains still form the Appalachian region of America today. Here you can see Pangaea, the supercontinent, and the equator, where it would have existed at 245 million years ago. Now 170 million years ago, that supercontinent is starting to break up. A new ocean is being created, kind of like the Red Sea zone that we saw in East Africa today, and the location where divergence is starting to occur. More mountains created, or more islands created by subduction on the west coast of North America. Those islands are joining up with North America to build the western states as North America is moving away from Eurasia and from Africa. 85 million years ago, we're starting to look a little bit more like North America. I didn't mention before, but this white zones over the continents represent shallow oceans that existed over these regions in times when the Earth was warmer and we had sea level rise that was quite significant. 65 million years ago, this is the time around when dinosaurs went extinct. 40 million years ago, it's looking a lot more like it does today. 8 million years ago, and then here's a more recognizable North America 3 million years ago, and then finally much more recognizable structure of the place that we all live today. So you can see quite a bit of change has been accomplished by plate tectonics. Let's go back and go through it real fast one time to appreciate the changes. And that is how plate tectonics works. Pretty impressive stuff. All right, have a nice afternoon.